To an untrained eye, a raw binary dump of a Windows executable appears to be chaotic, random noise. But the Windows operating system does not read noise. It requires a specific structural framework to translate these bytes into a functioning process. That framework is the Portable Executable, or PE, architecture. It is the universal blueprint for how Windows files are organized on disk and loaded into memory. The OS loader uses PE metadata to map a contiguous block of raw data into isolated executable segments within the system's memory. By parsing this specific text dump, we can reconstruct that map and identify the intended behavior of the software. Navigating through the section headers, a unique string appears in the table, .acepack. Navigating the PE format is the baseline for forensic analysis. It provides the structural context required to determine if a file is exactly signature.
This is followed by a plain text DOS stub. This program must be run under Win32. This stub is a historical artifact from early computing. It exists solely to ensure backwards compatibility, preventing the file from crashing on an obsolete DOS system. Modern execution begins at the PE signature, which marks the start of the file's actual headers. Directly below these headers, the file declares its section table. In this dump, we can identify several standard section names. The code section, or .text, contains the executable CPU instructions the processor will run. The data section acts as the storage area for the program's initialized variables. The .idata section contains the import address table, which links the program to the external functions provided by the operating system. These headers and tables are the instructions the OS follows to isolate and prepare the code for execution. Now we return to the .aspect section we identified earlier. Standard compilers like MSVC or GCC do not generate a section with this name during a normal build process. ASPAC is an executable compression tool. It is used to wrap a program inside an obfuscated layer. This means the code section we mapped earlier has been compressed and encrypted. The true instructions are currently unreadable on the disk. To make the file functional, the packer attaches a small, uncompressed stub of code to the beginning of the executable. When Windows runs this file, it executes the packer stub first. The main program remains dormant in its compressed state. The stub's primary job is to decompress the hidden code back into the system's memory. Once the data is expanded, the stub rebuilds the program's internal memory pointers to make the code functional. Finally, the stub hands over control by jumping the instruction pointer to the original entry point of the newly unpacked code. Only at this moment does the actual program begin to run. Packers ensure the true executable code only exists dynamically in memory, rather than statically on the disk. We can still deduce the program's intent by examining the .ida section at the end of the text dump. The import address table lists every external Windows function the software requires to operate. This dump contains references to kernel32.dll, the command load library A, and get proc address. A packed binary cannot rely on the standard Windows loader to link its functions automatically, because the code that needs them is still compressed. Instead, the packer stub must manually import these functions at runtime. It uses load library A to pull a DLL into memory, and get proc address to locate specific commands. Finding these specific imports in the .ida section provides the mechanical evidence that runtime unpacking is occurring. Beyond the packer's own requirements, we see other readable imports, reg set value A and shell execute A. These reveal the software's capabilities. Reg set value A is used to modify the Windows registry for persistence, while shell execute A allows the file to launch secondary processes. We also find window from point, which indicates the software is designed to interact with the user's interface. Even when the primary payload is obscured, the import address table provides a high-confidence static profile of the software's true capabilities. Static analysis is the study of the container that holds the code. This shows the difference between a standard executable and the complex multi-stage memory map we just uncovered. Parsing the PE headers allowed us to identify a deliberate defense mechanism. The .ASPAC anomaly and the presence of dynamic linking APIs confirm that the file on disk is only a fraction of the program's true footprint. However, static analysis has reached its limit.
Because the payload is encrypted, we cannot see the specific instructions it will execute.
The next phase of the investigation requires dynamic analysis. By running the executable in a controlled debugger, we can watch the stub decompress the data in real time. Once the code is fully expanded in active memory, forensic analysts can dump the payload and analyze the true program, neutralizing the Packer's deception.